So welcome back to part 3 of lecture 22. When I introduced the term of multiplicity, that might have reminded you of kind of your first linear algebra course, Math 1B03, where we used the term multiplicity. And I just want to kind of take a little kind of detour here to kind of explain that connection. All right. So in Math 1B03, we introduced actually two types of multiplicity. We introduced like the algebraic multiplicity and the geometric multiplicity. And you may want to go back and look back at your notes. But what the algebraic multiplicity was it had something to do with looking at the characteristic polynomial of your matrix, okay? And the geometric multiplicity was equaling to the dimension of a particular null space. So these were terms introduced in 1B03. And I just want to kind of explain the connection to 2R03. So what we call the algebraic multiplicity of lambda is actually what in 2R03 we call simply the multiplicity of lambda. Or another way is saying that it's the dimension of the generalized eigenspace. And the geometric multiplicity of lambda is actually equal to the dimension of the eigenspace of lambda. So over on this side, we're looking kind of at, using terms and using kind of ideas of operators and subspaces. And over here, we looked at things coming from a matrix. And it's not clear why we should have an equality on the first line because we haven't introduced determinants. And in fact, we're not going to do it in this course. But at the end of the book, you can actually see why these two things are the same. But just when I'm using the word multiplicity in this course, you want to think of algebraic multiplicity. What we call geometric multiplicity was just simply the dimension of the eigenspace. But I want to point out that a couple statements that we had in 1B03 where I didn't spend too much time on the proof actually become very simple now based upon what we've done. For example, we stated that for any eigenvalue, the geometric multiplicity of lambda is less than or equal to the algebraic multiplicity of lambda. And this now follows simply from the fact that we're looking at subspaces, right? So this follows from the fact that the eigenspace of an eigenvalue has to be strictly greater than the zero subspace, and this is contained inside of the generalized eigenspace. So the dimension of this is bigger than or equal to this, which is bigger than or equal to 1. Okay, so that result now just follows quickly from what we've done so far in this course. And the other thing that you may remember is that we proved that A is diagonalizable if and only if the geometric multiplicity is equal to the algebraic multiplicity. And let's try to prove it using kind of the terminology from this course, right? So what it means for a matrix to be diagonalizable, it's the same thing as saying that the linear map let's call it the linear map associated to this matrix is diagonalizable, right? But we know when exactly a matrix is going to, or a linear map is going to be diagonalizable. That means that V can be written as the direct sum of its eigenspaces, right? But we also know that V can be written as a direct sum of its generalized eigenspaces. That's what we just proved in today's class, or earlier in the lecture. But this can only happen if the eigenspace of each of the eigenspaces are equal to its generalized eigenspace, right? So this happens if and only if the eigenspace of lambda I is equal to the generalized eigenspace of lambda I for all I. And then this here is saying these two dimensions are the same, which is saying that the geometric multiplicity of lambda I is equal to the algebraic multiplicity of lambda I. Okay, so something that in Math 1B03, I avoided the proof. If you took it with me, or depending on who taught it to you, you probably didn't see the proof. But now once you have all of this language from Math 2R03, the proofs actually become straightforward. Okay, so just to kind of get things set up for the next part of today's lecture, I just want to quickly introduce what a block diagonal matrix is. So a block diagonal matrix is like this giant matrix, an n by n matrix, where along the diagonals we have a bunch of matrices, where each AI is a square matrix on the diagonal. So here is an example of a block diagonal matrix, and let me just circle the blocks here. So you want to think of this as a 3 by 3 matrix. Here we have a 1 by 1 matrix, and here we have, we didn't want that as a circle. It's so bad that my writing is so bad it thinks a square is a circle. I'll try that one more time. Well, we'll leave it like that. Here are the blocks of my matrix. Okay, so this would be an example of a block matrix. So when we come back, I want to kind of talk about the following theorem, which will allow us to write the matrix of any operator over the complex number as a block matrix. Okay, I'll see you in the next part.